In this example, we learn a little bit about how a transmission electron microscope works, and we use some parameters from that microscope to figure out how fast the electrons in that microscope are traveling. So a transmission electron microscope forms an image by sending a beam of moving electrons through a sample. Okay, how a regular microscope works is light is sent through a sample, but in a TEM or a transmission electron microscope, we're sending a bunch of electrons. And the electrons accelerate through the microscope at a certain speed. And what gives them that speed is a potential difference of 2.5 kilovolts. Okay, so the units are volts, so that's telling us that we have a delta V of 2.5 kV, where K is kilo, so that's 2.5 times 10 to the 3 volts. Okay, so the part of the microscope that is responsible for moving those electrons really fast, okay, that has two parts called an anode and a cathode. Where's the cathode here? Well, they don't mention the cathode, but those are the two parts of the accelerator for the electrons. And so what the problem is stating is that through those two parts of the microscope, the potential difference there is 2.5 kilovolts. And the electrons, let's say, are moving this way. And the question is, how fast are they traveling when they pass, if they're initially at rest? So you're going to see some keywords here, and they're going to kind of bring you back to the first example that we did in this chapter, where we were dealing with energy, and we were using the concept of work and change in kinetic energy and relating that to the change in potential energy. So we're going to be doing that again, but now instead of expressing delta U, we are going to be using delta V. And so how do we go from delta U to delta V? Well, we know that delta V is delta U over Q. So we're going to be using this relationship. But what do we know about delta Q? Delta U. How does delta U relate to speed of a particle accelerating in an electric field? Well, we saw earlier in this chapter that we have three different definitions for work, right? We have work is FD cosine theta, which F is QE, okay? We saw that work is also equal to delta K, K final minus K initial, and then finally, work is also equal to negative delta U, okay? Where delta U is U final minus U initial. So now hopefully you can see, right, the relationship we're going to be using to find the velocity, because we remember that kinetic energy is 1/2 mv squared, so that's going to give us our velocity term. And then this delta U part is going to come into play right here. So I think what I want to do first is I'm going to express delta K in terms of delta U, right? So delta K is going to equal negative delta U. And we're not given delta U, but we're given delta V. And so I'm going to use this relationship here to further express delta U as Q delta V. Okay, right? All I did was move the Q in front of the delta V here. So now, K delta K, well, that's kinetic energy final minus kinetic energy initial. And I am told that we're starting off initially at rest. So initial kinetic energy will be 0. So finally, I can write down what KF is. I can write down all of my values. Maybe, yeah, let's wait to write the values until we express VF, okay? Which is what we're looking for, how fast the electrons are traveling. So let's solve for VF. And there's a square root there. And you may be wondering, okay, we have a negative sign under the square root, but that's okay because we have a couple places where we could have a negative sign come into play to negate that first negative, right? So let's plug in all of our values now. -2 Q. So what are we going to use for Q? Well, that's the charge of an electron, right? Because we are accelerating electrons through the microscope because it's an electron microscope. So that's going to be the charge of an electron, which is 1.602 times 10 to the minus 19 coulombs. And delta V is 2.5 times 10 to the 3 volts. And finally, mass of the electron. If we recall from the previous example, it wasn't given there, but I believe it's 9.11 times 10 to the minus 31 kilograms. So we plug this into the calculator, and my numerator comes out to be 8.01 times 10 to the minus 16. That's coulombs times volts. Denominator, 9.11. And that is going to be okay, take the square root of that. Comes out to be 2.97 times 10 to the 7 meters per second. That was coulomb, volt, kilograms, all square rooted. Plugging in the units for volts, all of that will come out correctly, and we get meters per second. So, you know, all in all, this is a type of an example that it's a lot like, you know, a word problem. It gives you a lot of extra information, and all you really need from it is very little. You need the knowledge of what this potential 2.5 kilovolts means, right? And that is your delta V. And then second, you need to know the relationship between delta V and delta U. And then third, you go back to the relationships between work and potential energy and kinetic energy, and you use that to bring in delta K so that you can find the velocity. Okay, so it really wasn't too bad, and if you look at it, it's extremely similar to the very first example that we did, except now we're expressing the energy in terms of a potential, okay? And we're just talking about, you know, an arbitrary electron in a beam of electrons. And so that is the power of speaking about potential, is that you can speak more generally about situations instead of always having to say that you're tracking a single electron in this beam, right? We're tracking all the electrons in this beam, and each electron is accelerating through a potential of 2.5 kilovolts and being given enough energy to move them at 2.97 times 10 to the 7 meters per second. Okay, so that ends this example 17.6, transmission electron microscope.